so this is our honors chemistry lesson video for section 13.3, and hopefully if you powered through all the chapter 10, 11, and 12 ones, you're noticing that this chapter is a lot easier to get through. So in section 1 we focused on gases, in section 2 we focused on liquids, and now we're going to focus on solids. This is actually the shortest section because there's really the least amount of things to really talk about with solids. So the general properties of solids reflect the orderly arrangement of their particles, so notice they're kind of all nice and orderly, and the fixed locations. So a solid cannot float. Now the particles are moving, but they just vibrate in their fixed locations. They can't flow past one another. So this is due to strong intermolecular forces. When you heat a solid, its particles vibrate more rapidly. As their kinetic energy increases, eventually they vibrate so much that they can break free of their fixed positions, and then it can flow because it's a liquid, so it has melted. So the melting point is the temperature at which a solid changes to a liquid. So in a crystal, the particles are arranged in an orderly repeating 3D dimensional pattern called a crystal lattice. The smallest group of particles within a crystal that retains the geometric shape of the crystal is known as the unit cell. So any solid that has a 3D repeating pattern called the crystal lattice is a crystal. So it doesn't have to be like a gemstone. Like yes, gemstones are crystals too, but so is ice, so is salt, so is sugar, things that you don't think of. So is cupric sulfate. You know, I'm sure that was the first thing you thought of when you thought of a crystal, right? And then the smallest group of particles that retains the shape is the unit cell. So kind of think of it as this whole wall is made of cinder blocks. One cinder block is kind of like the unit cell of a crystal. So ionic solids have high melting points, which is above 300. So remember, we know something is ionic if we subtract the electronegativity values and it's greater than 2, or if it's a metal and a non-metal. That's a good rule of thumb to use. Molecular solids have low melting points, which is below 300 degrees Celsius. So remember, molecular solids, those are usually made of only nonmetals. And then not all solids melt. Some just decompose, like wood. Like I can heat wood and heat wood and heat wood, and eventually it's going to catch on fire and decompose into ashes. It's not going to melt into liquid wood, although that would be super cool if that did happen. Also, some substances, like a mixture like chocolate, they don't have a specific melting point. It kind of starts melting and melts over a range. That's a characteristic of some mixtures because they have lots of different substances together. And then allotropes are two or more different molecular forms of the same element in the same physical state. A common example is carbon. You have diamond, graphite, and buckyball. So diamond has carbon atoms bonded in a tetrahedral shape. So you know what tetrahedral is. You have the one pointing up and then like the tripod at the bottom is very, very strong bonding. And it looks like that. You know what diamond looks like. However, graphite is also made of carbon atoms, but instead of being in a tetrahedral shape, it's like in a honeycomb shape. So it's these 6-membered rings, and then it exists in different sheets or layers. But still, it's only carbon, so that's why they're allotropes. And then, of course, buckyball is carbon 60, so there's 60 carbon atoms, and they form a ball shape with alternating 6 and 5-membered rings. Other examples include phosphorus, like you have white phosphorus, red phosphorus. Sulfur, you can have S or S8, and oxygen. You can have oxygen we breathe like O2, or you can have ozone, which is O3. So those are all allotropes. So not all solids are crystals. An amorphous solid lacks an ordered internal structure. Examples include rubber, plastic, and asphalt. Glass is an amorphous solid that is a supercooled liquid. Okay, I like you to know both of those terms. It's an amorphous solid that is a supercooled liquid. Glass is formed by cooling a liquid into a rigid state without it crystallizing. So it's not a crystal, that's what makes it an amorphous solid. So, section assessment. Boy, this is the fastest lesson video I think I might have made the whole time. So in general, how are the particles of a solid arranged? They are in an orderly arrangement. Orderly arrangement. You could also say they're in fixed positions. Either one's fine. Number 2, how do allotropes of an element differ? Well, they have the same types of atoms, but they differ in the bonding arrangement. Okay, so they differ in the bonding arrangement, how those atoms are bonded together. And then number 3, how do the melting points of ionic solids generally compare with those of molecular solids? Ionic solids tend to have higher melting points than molecular solids. Ionic solids tend to have higher melting points than molecular solids. Whew, that was so nice and easy. All right, and so if you'll stick around and watch the very last one, which is 13.4, we will focus on phase changes, going from one state of matter to another.